Ladies and gentlemen, today I'm thrilled to share with you an innovative project born out of a deep personal motivation and a pressing environmental challenge. Let me introduce you to ThermoSync, a project that aims to elevate comfort and illuminate intelligence in our lives. Here's the topic outline for today. In 2024, Singapore is set to increase its carbon tax by a significant amount. This impending change underscores the urgent need for a smart system that enhances energy efficiency, mitigates environmental impact, and reduces electricity expenses. It's not just about economics, it's about sustainability and responsibility. The main motivation behind ThermoSync stems from a very personal place. The escalating electricity expenses, driven by our growing dependence on electrical appliances, have become a financial burden on my family. Determined to alleviate this strain and avoid perpetuating a constant financial challenge, I embarked on a journey to find innovative ways to enhance energy efficiency while maintaining comfort in our household. ThermoSync achieves this by integrating an intelligent system that features an LDR for adaptive lighting, a temperature control system with two potential meters to set the temperature and fan speed respectively, and finally a motion PIR sensor. For the peripherals used for GPIO, timer, and ADC configurations, for interrupts, external USART and ADC were used. And finally, for serial communication, UART and I2C protocols were used. Here's the system block diagram from input subsystem, processor subsystem, and output subsystem. Here's the Tinkercad design, the schematic for the transceiver and receiver. Now let me walk through the computational thinking behind ThermoSync using a simple flowchart. When a user enters the room, the motion sensor detects their presence. This triggers the system to check the ambient light conditions using the LDR. Based on the information, it adjusts the lighting accordingly. Simultaneously, the temperature control system assesses the room temperature measured and the temperature set and makes the current and necessary adjustments for optimal comfort. To bring this to life, let me now showcase a brief demonstration of ThermoSync in action. Let's begin on the demonstration for ThermoSync. So if we look at the LCD below, it is prompting the user to enter the household. Once we enter the household, it is motion that is detected by the PIR sensor, which then initializes and activates the program. So if we can see, the LCD now changes to show the temperature. We can now also use the push button when we press it to change from temperature to fan speed to LED or the light setting. So once we go back to the temperature setting, we can see the temperature set and the temperature measured, which is both at 25 degrees Celsius respectively. Since the difference in temperature is within the range of 0 to 1 degree Celsius, the tri-LED as shown above in the main breadboard is shining the color blue, indicating to the user that the temperature difference is 0, indicating or implying that the temperature set has been reached. And if you look above the main breadboard, we have two potentiometers to set the temperature and fan speed respectively. However, the fan speed dial is at its maximum setting, while the DC motor is at 0 RPM. This indicates that the programming used shows that we had used an if condition statement where regardless of whether the fan speed dial is turned on and off, as long as the temperature set is in equilibrium to the temperature measured, then the DC motor no longer needs to be turned on, which implies that it is able to conserve energy as the DC motor is no longer being activated and wasted. So let's go over and see that, let's say we change the temperature to 21 degrees that we desire. As you can see, without adjusting the potentiometer for the fan speed, the DC motor is turned on and is at its maximum setting. So now it is acting as an air conditioner to decrease the temperature measured to the temperature set. So let's say we adjust the temperature measured to the temperature we set eventually. The tri-LED now shines the color blue, which is different from the color green because the temperature difference is now within the range of 0 to 1 degree Celsius. So if we look at, let's say, a difference of temperature right now, and we look at the fan speed, we are able to see in the second display of the LCD, the fan speed. And if, let's say, we are able to adjust using the potentiometer to half the RPM we desire, or we can even turn it off. So now moving on to the next setting, which is the light monitoring system. Studies have shown that different colors of light at different times for human beings can help be less taxing towards the eyes of humans. So let's say it is nighttime, the color that is chosen is the color red. When the light sensitivity shown on the LDR changes, it is now evening and the LED shown is now yellow. For the time of afternoon is the color white, and for the time in the morning is the color blue. And when it reaches peak hour, which is at noon, since at peak hour, the intensity of the light shown from the sun is at its maximum, there is no need to activate the LEDs. Thus, we are able to conserve electricity in this instance. So now let's look over at the transmitter code. where over here I've declared all of my constants, my variables, and here we have the method for interrupt for receive, interrupt for external interrupt, which is for the push button and the PRS sensor respectively, the ADC interrupt to do all of the calculations and if condition statements. Then we initialize USART, start the conversion for ADC, external and GPIO configurations, which is all within the main method. Inside the main method, we have a while loop to be able to adjust the tri-LED and the LCD respectively. And below, in highlighter, we have the LCD functions using I2C. So now going to the receiver, we have the constants declared, the clock speed, variables. For interrupt, we have timer 1, interrupt for USART transmit, interrupt for ADC to start the conversion. We also initialize USART, and in order to actually start the ADC conversion, we use the ADC method, and it is all also declared within the main method, and we have the configuration for timer. Finally, one special thing is that for the PRS sensor, normally it is now currently generating a pulse of 0 for the output. However, we are able to use EDSS to toggle it such that when it detects motion again, indicating or implying that the user has left the household, it automatically deactivates the system, as you can see. And now it is prompting user to enter the system again. So once we enter the system again, it is able to initialize the program all over again, as you can see.